notice to everyone, and this can be viewed asynchronously if you wish to do so. All right, to start, what is Pandas? Pandas is a Python library, open source from Anaconda that you can use for data analysis and manipulation. The reason Pandas is so useful is because of the power in its application. Even though it can seem daunting, it is pretty easy to use. Obviously, through practice, one can learn the ins and outs and become quite adequate at utilizing the Python library that is Pandas. When working with large data sets, whether that's geological data, business analytics, I'm sure many of you have seen it in your CS or data science classes. Any of these large data sets are easily transformed, manipulated, and analyzed using Pandas. All right, to get started, we showed this to a few of the people who jumped in early with us, but we want you, if you can, to download Anaconda. This will install the libraries utilized today that are NumPy and Pandas, and these are essential in use in the Jupyter notebooks. The GitHub repository is linked below. Feel free to go in there and grab the notebooks associated with the IPython libraries, either the empty notebook or the filled notebook. For those with us, the filled notebook is recommended for ease of use and following along, but the empty notebook is great practice, as you will see in the following slides. And you want to be able to download the movies data set, as this is the data that we will be working with for the rest of the session today. So the Jupyter Notebook. Jupyter Notebooks are an essential part of running any of the Python code that you're going to see today. They're great for ease of use. It's an execution environment that supports our Python programming. Here, you're able to easily visualize the data sets, manipulate the data through cleaning and transformation, perform certain numerical simulations, whether you're using the Jupyter Notebook to analyze data for a research project, or trying to perform simulations related to business analytics and marketing, and much more. So to create a notebook, you're going to launch the Jupyter notebook from the Anaconda homepage. Then you'll navigate to the desired directory, click New, and then Python 3, your coding language of choice. So here is just a schematic of what you're going to do when you open your Jupyter notebook. Depending on what your directory is, you can locate it like as we did through downloads DS3 and Kaggle. And once you run that new notebook in the right top right hand corner, you'll click Python 3 as your code and you'll be good. All right, importing libraries. So make sure the movie CSV is in the same directory as your notebook. This is pretty important for ease of use, but can be done otherwise. So to begin, import Pandas and NumPy in your first code cell. These are the libraries that are crucial to a process, working with the data from here on out. Running the cell is easy. At the top of your notebook, you'll see the run command. You can just click it, and that will run your code as long as the syntax is correct and everything is running smoothly. The best way, and the way that all of us here at the Kaggle Workshop Committee, you do it, is to hit Shift and Enter at the same time, and automatically it opens a new cell below the one you're working with. Okay, importing the data. Reading the CSV into your Jupyter notebook is super easy. The code is as follows. So first you want to define your variable. Here we define our data frame as df, and you want to equate that to PD, which is Pandas, and read the CSV using quotes, and in order to visualize the first 5 rows of our data frame, we use df.head just to get a look at the data and become generally understanding of what's going to be going on in the future. All right, heads or tails. As you saw before, we're going to be working with functions such as df.head, df.tails. These are used for easily displaying the first or last few rows of a data frame. Placing any integer value will produce the amount of rows. The default is 5. These allow for quick confirmation that data was loaded successfully and that you're expecting, what you expected, or you are getting what you expected. All right, exploring the data. We want to take a look at what exactly we're working with here. So there are various functions that allow one to, look at what data you're working with in a Python data frame. For example, df.shape returns a tuple representing the dimensionality of your data frame. In the top right corner, I listed a definition. So a tuple is a finite order list of elements, in our case, rows and columns. So you'll be getting the rows and columns of your data frame. Another useful function is df.dtypes. Returned is a series with the data types for each of your columns in your data frame. Try calling these functions in your notebook. I'll give you a minute to do so if you are running an empty notebook. If not, you could just shift enter on your associated cell. All right. So here is the output you should be seeing. df.shape returns the tuple with the rows and columns of our data frame. As you can see, there are 16,744 rows corresponding to the different movies in our data frame. And the 16 columns are 16 variables that give us the information we want to know and we want to work with corresponding to each of those rows and consequently each of those movies. df.dtypes allows us to take a look into the depth of the data we're working with. For example, title is an object data type, whereas year is an integer 64. This means that you're just going to be getting a regular integer corresponding to that variable. Whereas IMDb column, which is, I believe the percentage, is going to give you a float 64. So after your integer value, you'll see the decimal points following those, and that data type is known as a float.
So now we're going to shift gears a little bit and kind of work on selecting data from the data frame. So we have a few methods for selecting a certain column. There's actually more than 5, but we're going to focus on the main 3, which we use during our data science classes. So the first method includes listing out the variable of your data frame, which is df in our case, and we're going to pass in a string, which is the column name, into the brackets. And doing so will give you kind of like a list that corresponds to the values within the column named title. And if we move on to the second method, it's pretty similar, but instead the column name is not in strings. So you're going to add a period after declaring the data frame variable and then pass the column name. And you'll also get the same result, which is something that looks like a list. And then for the third method, this is most commonly used in introductory data science classes. So it's by using the get method. And in general, Python methods have the format of the period, the method name, and then parentheses. So here you're passing the column name into the get method, which also returns the information from the title column. Yeah, so in order to select multiple columns, it's kind of similar, but instead you might notice that there are double brackets, and that's because in order to select multiple columns, you're going to have to kind of put in a list, and a list in Python is generally a brackets surrounding comma separated values. So if you were actually to not do the double brackets, you will get an error. So make sure you have the double brackets whenever you are selecting multiple columns. And so you might see that, the results kind of look different. So back to when we were selecting one column, you got something that looked like a list. And then when you selected multiple columns, you got something that looked like a neat table. So these two are two different data structures within Pandas. So the one to the left is called a series. so the one that looks like a list. And a series is basically a single list with indices on the left-hand side, and it's a one-dimensional labeled array. And as opposed to that, we have, when we select multiple columns, we get that neat data frame. So a data frame consists of one or more series, and it's in the two-dimensional labeled data structure. And if you remember, I said that if you don't have the double quotes when selecting multiple columns, you get an error. But if you were to put a single column name within the double brackets, that would work fine. So if you compare the first two pictures, so the first one is a series and the second one is a data frame, the only difference is that the first one has single brackets and the second one has double brackets. But just make sure that when you're selecting multiple columns, you only use double brackets. So now we kind of covered selecting columns, and now we're moving forward with selecting rows. So there are two main ways to select rows, and it's using the iloc and loc method. They both work pretty similarly in this case. So you're going to pass the index of the row you want within the iloc method. And unlike regular Python methods, iloc has brackets instead of parentheses. And if you're not familiar with how indexing works, so the first row has index 0, the second row has index 1, the third row has index 2, and so on. So rather than counting like from 1 to infinity, you're counting from 0. So by us passing in 0 in this method, we're actually retrieving the first row. So another example would be if we were to pass in, let's say, a 1, then we're getting the second row. And here you're getting a series as a result. So since in that case, loc and iloc worked pretty similarly, it might be confusing as to see when to use which. So when you are doing something more complex, like selecting certain columns and rows, it matters what you put into the method. So loc generally takes rows and columns based on the label that is passed. As for iloc, it retrieves rows and columns based on the indices passed. So on the right-hand side, we're using the loc method, and the loc method takes in labels. So the value after the comma specifies what column we want, and for the loc method, you need to send a label through. So if you were to put a number through instead of the value title, you would get an error. And on the left-hand side, we're using the iloc method, which takes in indices or integers. So that's why we have the number 2 after the comma. And if you were to pass in a string or a column name instead of an integer, you would also get an error. So it's important to know which one to use during which situation. And something very interesting about loc is that its slicing mechanism is a bit different from normal Python slicing. And so in normal Python slicing, it retrieves the indices from the start to stop, but excluding the stop, as opposed to loc, where it takes all the indices from the start to stop, including stop. So that's why in the first picture, you get items from indices 0 to 5, as opposed to iloc, where you get indices 0 to 4, because 5 is excluded in regular slicing. So to kind of help you kind of practice with the loc and iloc method and how they can be used differently, we have a practice problem for you. So we'll give you a few minutes to work on this, but we want you to use the iloc method and access the year Avengers Infinity War was released. and that corresponds to the item in the third row and fourth column. So some things to remember is that indexing starts at 0 and not 1. And as a hint, the format of using iloc is listing the data frame and then .iloc, and then specifying the indices for the row and for the column. So yeah, we'll give you a few minutes for that. And if you have any questions, just give us a message in the chat. All right, I think we can go ahead and move on to the next slide if no one has questions. All right, so what we're trying to look for was the item in the third row and fourth column. So that for the row, third row, that corresponds with index 2. And for the fourth column, that corresponds to index 3 because indexing starts at 0. So using the iloc method, the answer would be df.iloc 2, 3, and the answer is 2018. So now we'll move on to selecting multiple rows. Doing so, it's pretty similar to the, oh, never mind. So in order to do so, you're going to use the indexing operators, which are the brackets, following declaring the data frame, and then putting in the slice that you want. So the number before the colon specifies the start, and the number after the colon specifies the end. And with regular indexing, it takes all of the information between the start and end, but excluding the end index. So if we were to pass 0, 5, we would be getting rows with indices 0 to 4. And that is the same thing as df.head, which are the first 5 rows in the data set. And the second method is using the iloc method. The only difference is that you're using .iloc instead of just the brackets, and you would get the exact same results, which are the first 5 rows in the data set. And then the last method is with the loc method. And like I mentioned before, loc is different than normal Python slicing because it includes all of the rows from start to end, including the end. So you get the rows from indices 0 to 5. So this is not the same thing as df.head because it returns the first 6 rows of the data frame. So I know that was a lot of information, but we want you to practice with what you learned so far. So for selecting multiple rows, we want you to use the loc method and return the 5th to 10th inclusive rows of the data frame. And if you do have time, you can go ahead and try to get the same results using the loc and regular slicing methods. And before doing so, you might want to think about, how does indexing work, what corresponds with the first row, second row, and so on. And remember that we want 5th to 10th inclusive rows. So yeah, we'll give you a few minutes to work on that as well. All right, so for the solutions of selecting multiple rows, we were trying to get the 5th to 10th rows, including the 10th row. So the index that corresponds with the 5th row is 4, and the index that corresponds with the 10th row is 9. So, or at least with loc. So using loc, you would use the slice 4 to 9. And if you're using iloc or the regular slicing method, you would use 4 to 10. And that's because loc always includes the ending or the end index. So yeah, your results should look like that. It would return items from indices 4 to 9.
Awesome. Okay. So now we're going to move to another part of our presentation. So we're going to go through something called data cleaning. And data cleaning is the process of correcting error-filled values or filling in missing values. Because when you have a data set, you rarely have a perfect data set. And sometimes these error values can make your analysis like unmeaningful. So there's a saying called garbage in, garbage out. It's because your analysis can only be as good as the data going into it. So that's why before actually proceeding with an analysis, data scientists, they spend around 70 or 80% of their time cleaning and preparing their data. This seems like a lot of the time, but it's true because this is a very involved process, and you want to make sure that there are no flaws in your data when you're doing your analysis. Okay, so one type of data cleaning is dropping columns. So in this data set, we have a ton of different columns. So using the chat, can you all let me know if you see any columns that you think are redundant or we could drop? So yeah, anytime you guys want to, yeah, just drop it in the chat, and just any columns that seem like they would be fine to drop. Yep, I see unnamed 0. That is one of them. Any, or can we think of any others? Yeah, thanks, Blake. ID is definitely one that we want to drop. And the third one is a little bit tougher to see, but it's type. This one, you would only know if you check the entire data set. This one is 0 for all values, so it's not really too meaningful. So right now we can use the dot drop function, which is really helpful to drop columns, but it can also be used to drop rows. So so as you can notice, inside the drop function, we have some parameters. The axis parameter tells you whether to drop rows or columns, and the default is axis equals 0, and this drops rows. However, since we want to drop columns, we need to use axis equals 1, and this is something that we cannot have by default, because if it was default, then we'd be dropping rows here. And as you can see, the first parameter is a list of the columns that we wanted to drop. And whatever you put into the list here, it must match the column in the data table. So as you can see, unnamed 0 has a space there. If we did not put a space there, then Pandas would complain to us that it could not find that column. And we can verify that our data set has changed by checking the dimensions of it. So as you know, as Blake said earlier, df.shape gives you a tuple with the rows and the columns. And just to verify that no rows were dropped, we have the first coordinate, which is 16,744, the number of rows. And then the second one is 14, which tells us that 3 rows or 3 columns were dropped from before. Another parameter to know is in place. So in place tells you whether to do an operation in place, like to permanently change the data set that you're working with, or to just return a copy. So doing an operation in place will change your data frame. And sometimes this is not what you want to do because you want to refer back to that original one. But since we're just dropping these permanently, we can use in place equals true. And next up in a data set, a lot of the times you're going to have null values because a lot of the times it's humans that put this data in, and there's going to be some missing values in there. So our first approach to getting rid of the NaN or not a number values is by using the drop NA function. So as you can see here, we did df.drop NA, and now if we check the dimensions of that, it's 3,301 rows. So this is an example of why you need to understand the data set, because in this one move, we just lost around 11 or 12,000 rows. So this is not cleaning the data, it's destroying it. So you need to drop wisely according to what your end goal is. Because sometimes you might, although a column is, or although a row might not be perfectly full, it'll still have values with valuable data in them, which is why we can try a better approach here. So now we can specify some parameters to drop exactly what we want. So the default parameter in drop NA is how equals any. So what that means is how equals any means if any of the values are NaN or null, then you drop it. And then that's why, but in the previous step, for any rows, so for all the rows that had any missing values, they just completely dropped it. So the 3,000 rows that were remaining were perfect rows with full data. However, there are still some more rows that we can use that are valuable to us. So we can try doing this one thing here to see if there's any rows with fully missing values. So by dropping where all of the values are null and having in place equals true, we can see that the dimensions were actually the same as before, 16,744 rows. So that means there were no rows with fully NaN values. So now we're going to use a scenario where we want to see what type of rows which rows to how to cut down the data table. So if your scenario said to create a distribution of movies comparing the IMDb ratings of movies across the major streaming platforms, our goal here would be to have the values, the rows where all where their IMDb values were numbers. So they should not be missing. So that's why we will drop, and we'll use this parameter called subset. And subset tells you which columns to look at. And we would drop rows where it had an empty IMDb value. And as you can see, from the dimensions, it dropped around 600 rows here. So this is much better because you have a lot more data, and more data does usually mean a better analysis because there's less deviation, or there's less deviation and more certainty in your data. So now another scenario is to create a distribution of the average rating, which we define to be the mean of the IMDb and Rotten Tomato ratings on Netflix movies. So does anyone have any idea on how we can drop the irrelevant rows here? So if someone can put in the chat, how would we edit this line above? So what subset of columns would we want to use here? Awesome, Aditi. Yeah, perfect. So here you want to, since you want the mean of the IMDb and Rotten Tomatoes ratings, you want to make sure that whatever movie you have, it has a Rotten Tomato and IMDb rating. Otherwise, it will not. Otherwise, you might have a missing value, and your analysis will be a little bit off. So that's why we want to use subset equals IMDb and Rotten Tomatoes. And to Alexander, you said, what does subset do again? Subset it's a list parameter that you pass to drop NA, and it tells you which columns to look at. So now this line of code, what it did here is it looked at every single row and dropped any row that had missing values in either column. So the remaining data set is 5,156 rows, and this means that these 5,156 movies, they have both an IMDb and Rotten Tomatoes rating. Okay, so another part of data cleaning is renaming columns, because sometimes the column names can be ambiguous. And the first method we usually use is rename. And this is used for changing only a few column names. So as you can see in the example, we used df.rename, and the parameter here is it's a dictionary. So you use ordered pairs, and they're separated by colons here. And as you can see, we're changing age to age rating because that makes it more clear. Since the age rating is like PG-13 or R, it's like what age is suitable to watch this movie. And then we change runtime to runtime in minutes, so it's more specific. And as always, if you want to permanently change the data set, you can do in place equals true. Here we didn't do it in the first example because we wanted to do it in the second example. But this would be a case where you could totally use in place equals true if you want to keep the column named that way for permanently. And the second way that we can do it is using the attribute .columns. So if you just type in df.columns, you'll get an index object, which is it sort of has a list of all of the column names. And in order to so this is not really a method, this is using an attribute. So if you set the attribute to a new list of the strings of all of the string values of the columns, this will permanently change the data set. But the crucial thing here is that order matters. So a good tip is to do df.columns before, and then get all of the columns, the names of all the columns, and then change exactly what you want to change when you type it out. Okay. So yeah, no, again, order is really important, because if I switch the year and title ones in my line, there would have been movies under the year. So there could have been Inception, The Matrix, and Avengers under the year column, and then 2010 under the title column. So it wouldn't make too much sense. So that's why the order is really important for .columns. Okay, next up is data formatting. So in our data set here, this is actually something that I made a mistake with when I was working with the data set. So I was trying to sort movies by Rotten Tomatoes, but when I was sorting movies from worst to best, somehow the 100% the 100% movies were coming at the end, were coming at the beginning, so they were somehow the worst. And when rating from best to worst, the 99% movies were at the top. So I knew there was something wrong here. So looking at the data type of the values in the Rotten Tomatoes column, I realized that these were all strings. So with strings, sorting is a little bit different. So intuitively speaking, with integers or floats, 100 would be greater than 99. But with strings, they compare each digit. So 100% is actually less than 99%. And this might cause some headaches later. So we need to fix this if you ever want to sort by Rotten Tomatoes. So a good way to do this is by taking the Rotten Tomatoes column, and by doing .str.strip. By doing .str, this accesses all of the string properties within each of the values. And then we're using the strip method of strings to take out the percentage. Because initially the ratings were written as like 87% to 90%. So we want to take out that percentage because that's the first step of converting it into a numerical format. And then after that, we're indexing just that specific column. We're doing df of Rotten Tomatoes. And we wanted to change, we're basically casting everything to a number, to a numeric value, which is what the pd.toNumeric value does for us. And in this case, you would not need an in place equals true because you're permanently changing that df of Rotten Tomatoes column. But in other examples, as you'll see later, in place equals true, like for methods, it would change whether it returns a copy or whether it permanently changes the data set. Okay, so next up we have something called conditionals. And conditionals are a really great tool for querying your data frame and filtering out any information that is not really necessary. So if I wanted to see which movies were on Disney Plus, I could use the query df of, and then the column name is Disney Plus, and I could say equals 1. Because I noticed that in the data set, whichever movies were on a specific platform, they would have a 1 for that. They would have a value of 1 for that platform. So the code on the top, it shows a Boolean series of size 16,744. So a series is, as Carolyn said, it's a list of it's a list of values, and Boolean means true or false. And the true or false value is depending on whether this movie is a Disney movie or not. So all of the falses would be non-Disney movies, and all of the trues would be Disney movies. But this series here is a little bit non-intuitive. You can't really see what are the names of the movies. You only see the indices. So we can work around this by making a data frame using that conditional. So if we query df of that Boolean series, we will get a new data frame, and we can call that data frame Disney. And using the .shape method, you can see the dimensions, and our data set only had around 564 Disney Plus movies, which could be because it's a pretty new platform. So you can always use the comparison operators, which are equal to, not equal to, less than, greater than, and less than or equal to, greater than or equal to for comparisons. And if you want to combine multiple comparisons, you would use the Python bitwise operators. So use the ampersand for and the pipe for or, because these are the ways, because you're comparing the bits, and using the words and or would not work here. All right. So now again, when it comes to strings, it's a little bit more complicated. In general, strings are tough to deal with. So here, when we're searching for strings, we want to use the .str.contains method, because if we look at the directors column or the genres column, there are several different genres in there and several different directors for each movie. And if we say select the directors where the directors are equal to a specific director, it's comparing the strings by themselves. So a movie may be directed by like Steven Spielberg, but if there's another director listed with him, that query would actually ignore it because that string is not equal to just Steven Spielberg. So that's why we need to use the dot contains method. So if we wanted to find all the movies that were directed by Steven Spielberg and were family movies or action movies, this would be a multi-step process. And even for the genres, since there's multiple genres, we would need to use dot contains because a movie may have multiple directors or genres. So there's two different ways to go ahead and attack this problem. And I recommend the top way because it splits your work into several different steps, and it's often more approachable that way, and it's easier to debug your code when you may have a problem. And every data scientist or programmer has to go through debugging, and it's a really important process. So that's why I recommend you use intermediary variables. So I'll explain the top code. So the first line says director equals data frame of directors dot str dot contains Steven Spielberg. So what this is doing is this is going through the column directors, and it's checking every single value in that column, and it's seeing if it's going to return a series it's going to return a Boolean series that is true or false, and it's true if it contains Steven Spielberg, false otherwise. And then similar thing for the genres. If the genres contains family, then it would be true. If it contains action, then true, and otherwise false. And then reading the question, going back to the question, it says the movies directed by Steven Spielberg and were family movies or action movies. So here we would be combining the comparisons, which is where the bitwise operators come into play. So we would do data frame of, and then director, because that was our series, and the ampersand. And then we would use parentheses here because we want to, because the and takes precedence over the or, but we want to make sure that it's in either genre. So then we would do family genre or the action genre. And once you do that, you would get the same result here as if you condense into one line as well. So you would get all of the Steven Spielberg movies that were family movies and action movies. Awesome. So yeah, if anyone has any questions, please drop them in the chat, and my fellow members will help you out. So here we have a practice problem on conditionals. So you are holding a club social virtually through Netflix party next Friday. As all of your members are adults, you choose to watch a movie that is suitable for 16 plus or 18 plus. So this movie doesn't do MPAA ratings like PG-13 or R. So you'll be looking for 16 plus or 18 plus. You'll also want to watch a comedy movie that came out between 2000 and 2016, inclusive. Also, you don't really have high expectations for this movie. Anything rated above a 5.5 on IMDb is perfect. Create a data frame called social that has all of the possible movies that satisfy your criteria. So I'll give you guys like 5 minutes to work on this, and if you have any questions, just reach out to us and we'd be glad to help you out. Okay, since we're a little bit constrained on time, I will go ahead and move on to the next slide. I hope you all have given it an attempt, and yeah, let's see how to do this problem. So this problem is one that I highly recommend splitting into different steps, because honestly, like I mean, both of these ways, they give you the same code or the same data frame at the end, but I like doing the second option, doing it all in one line is super confusing, because the parentheses are just extremely hard to pair together. So when I was doing this, I preferred doing it in several different steps as well. And so going back to this problem, the reason why we do DF, we make a series for just the Netflix movies is because we want a Netflix party social, and we do that by saying DF of Netflix is equal to 1, and then since age rating is it's a string column, you can tell because the age ratings look like 18 plus, so that could only be a string. So we want to either have a 16 plus movie or an 18 plus movie. So we could have an ages series that combines these comparisons and combines these criteria together. And then we have genres, because we want we want the genre to be just comedy. And then we have the year range as well. And note that we said that we wanted the movies to be between 2000 and 2016, but inclusive. So we would end up using the greater than or equal to and less than or equal to there. And the rating should be greater than 5.5. And just putting all of these together, you have DF of all of these series. And since these are all criteria that we wanted, these were all criteria that we wanted to satisfy, it would be an and here. And you'll get a data set of 108 options, 108 rows. And your top movie here is Silver Linings Playbook. Okay. So now we'll go into sorting. Sorting is also a really useful operation, because sometimes you want to know what is the most popular thing, what is the least popular, what's the best, what's the worst. And when it comes to movies, this is no different. We really want to see which movies are great, which movies are not so great. So we can use a sort values function here. And this is a super useful function. All you have to do is give it a column, and you can say whether you want so the different parameters here are, so there's by equals. So by equals, you give it a column name that you want to sort it by. And then there's an ascending parameter. So by default, ascending is equal to true. So your data will be sorted from least to greatest. And on the left, I didn't need to put ascending equals true, but I just wanted to put that explicitly there. And if you want descending, there is no descending parameter. You would have to just say ascending equals false. And so as you can see, on the left here, we have ascending equals true. So we have the Rotten Tomatoes from lowest to highest, and then we have on the right, we have the certified fresh movies from highest to lowest. So what if you wanted to sort multiple columns? This is no problem here. We can just pass a list to the by parameter. As you noticed before, we just passed the name of one column to the by parameter. I think it was Rotten Tomatoes. So let's say we wanted to sort by IMDb as well. We would just pass a list here, and by doing so, it still counts as having one parameter. If we did not include the brackets there, this would create an error in our code. So by passing in this list, it tells you that we want to sort by Rotten Tomatoes first, and then if there happens to be a tie between two values, then we look at the IMDb ratings. And then ascending equals false, so we'd be looking at the best movies, then down to the worst. And what if we wanted to sort columns in different directions? So what if we wanted to find really old movies that were super good? We can totally do this as well. Just like the by parameter you could pass a list to it, you can do the exact same with the ascending parameter. So in this example, we wanted to find critically acclaimed classics. So we wanted to find the best movies from on Rotten Tomatoes, which would be ascending equals false, because we want highest values to lowest. And then looking at the year, we wanted the oldest movies first. So that's why we wanted year to correspond to ascending equals true. And here the order matters. So the first values in the list go together, and the second values in each list go together. So they're paired. And the oldest really good classic was A Trip to the Moon, and it was released in 1902. Okay, so now there's another practice problem for sorting. Yeah, so this sort of carries over from the previous question. So there are still too many movies to choose from your social. Since all 108 of the movies fit your criteria from before, you now decide to find the movies with the best Rotten Tomato ratings and IMDb ratings in that order. Create a social sorted data frame that has the top movies from the social data frame. Then use the previous strategies for indexing and slicing that Carolyn taught to find the top 10 movies which your club can vote on. Hint, the indices will not be in numerical order after you sort according to rating, so look for a method to reset the index. Okay, so this one is a little bit of a, this one takes a little more steps, but hopefully I'll give a couple of minutes since we're running short on time. If anyone has any questions, definitely just put it in the chat. And if you have a class or anything and you want to head out, you go ahead. Thank you so much for coming today. Yeah, thanks for stopping by, Alexander. Okay, so since there might not be enough time to do this problem, I'll just walk through how I would solve it if this was on an exam or something. So we're starting off with a data frame of 108 movies, so 108 rows. So now we want to find the best movies, or the movies with the best Rotten Tomato ratings and the IMDb ratings in that order. So using our previous the skills from the previous slide, we want to pass a list to the sort values function. And since it says Rotten Tomatoes ratings and then IMDb ratings in that order, the first item in the list would be Rotten Tomatoes, and the second one would be IMDb. And since we want best to worst, we would have to say ascending equals false. If we did not use the ascending parameter, then it would go from least to greatest, and it would be worst to best. And next up, if we tried, so I'll just go ahead and show this. So we sorted the values accordingly, and we get the data frame with all of the 100% values at the top. And if there's a tiebreaker, like for these ones at the top, like Bill Burr, Jim Gaffigan, the IMDb rating is the tiebreaker for them. So next up, we would try slicing, and using the strategy that Carolyn taught, the first parameter in loc would be the indices that you want. And since we want the first 10 and the stop value is inclusive, we would go from 0 to 9, and then we would try and then we want the title column. But since the indices on the left, as you can see in the left picture, are not zero, they don't have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. They're just random numbers. We need to reset this. We need to reset the indices. So next up, we can reset the indices, and we want to use in place equals true because we want to preserve these changes on our data set. And then next up, now we can try the same code from before, and we will get our answer. So we'll get the top 10 movies that we want to watch. Okay, so I believe, yeah, this was our last slide. Thank you so much for everyone who showed up today. And as Blake said, join DS3 on Discord and like us on Facebook, and stay updated with all of our events. And thank you so much for coming over.
Yeah, thank you guys for coming. Like Yash said, we have other events, datathons, online contests, podcasts, and more. So go ahead and check us out, follow us, and maybe even become a part of DS3.